So on number 48, here's the story. So you have to figure out the code on the battery. So is the top part of that battery the positive or the negative side?
Positive, I think.
Okay, and we're going to always work off the basic idea of current. So here's the story. So if your current is going to be going around like this, okay, so as that current is flowing through that copper wire, okay, so current's going through, it's in a magnetic field. You have to have two things. You have to have a magnetic field and you have to have a current. Just one by itself won't do anything. So you take your right hand, the current's going to be going down that wire. What's the magnetic field doing?
It's going in.
Magnetic field is going in, therefore the force on the wire is going to be acting to the right. So this is going to shoot this thing off to the right. Okay? So the force on that, and you're just going to use Bill sine theta, you don't have to worry about the sine theta part of it. So the force on it is going to be about 170 newtons. Okay? So then when you got that, then it's simple to find the acceleration. From there, you can use that equation. So on 48C, when you get done, that answer should be around 60 meters per second.
Whoa, whoa,
Oh, 48C.
oh, no.
What do you have, John?
Six the lake.
48C is around 60. What do you have?
Way faster than that.
You got sometimes sensor.
Yeah, that's
Wait. I think that's worse than
I got
mine.
one.
Probably.
I'm okay with it.
Now,
Wait, it's better.
let's talk
shit.
about.
It's just different.
I know you don't. But I feel like it might.
Now, let's talk about 46 because I promise you there's going to be a question like 46 on the test. I promise you. Okay? Mark my words.
Pinky promise?
Bro.
So, let's look at the big picture about what's happening on 46. So, you have two parallel charged plates. Yes, you've got to go old school, okay? And you're told that the top part of the plate is positively charged and the bottom part of the plate is negatively charged, okay? Cool. Now, what's the single most important word in problem 46?
Electron.
It's an electron. It's not a proton, it's an electron. Okay? It's an electron. Now, let's just say that the electron is only going through the electric field. Don't worry about magnetic field. Imagine you're getting ready for the electric field test. Okay? If that's the case, what's the electron going to do, Mr. Jones?
Going up.
What?
Because it's attracted to the proton and repels by the electron. Or the negative side.
So if there's nothing else, the electron is going to go up like this for two reasons. Okay? For two reasons, and two reasons only. It's being repulsed by the negative, and it's going to be attracted to the positive. So if I just shoot an electron through there, it will not go through in a straight line because there's going to be a force that's going to push that thing up. Okay? So what I've got to do is balance that out. So I have to have something to balance that out. Oh, let's have a magnetic field. So a magnetic field has the capacity to also exert a force on a moving particle. It has to be moving. Now, just think conceptually. Which direction does the force from the magnetic field have to act? Downward. So the force from the electric field is going to be pushing it up, which means the force from the magnetic field has to be acting downward. And what do you know about those two forces?
Equal.
They have to be equal. Okay? Because if one was bigger, one was smaller, hey, it's not going to balance out. Okay? And this is what we use. It's called a collimator. So what this does, and we set this up with two components. You have an electric field and you have a magnetic field. So if you can adjust those values, and again, it isn't like we can see an electron going through this, but what we do is we set up like some type of detection system. We shoot electrons through and you adjust the magnetic field or the electric field so that they end up going through in a straight line. Now, so here's the story. If you look at the information that you're given on 46, okay, you've got the separated by 1 centimeter, it's charged to 200 volts. You want to find the magnetic field and direction that will allow the electron to pass between without being deflected. Okay, now, here's the story. If you know the voltage and the distance, what can you find? You can find the value of the electric field, okay? Because you can use the idea that, oh, okay, you know the voltage, you know the distance, you can find the value of E. So you can go, okay, E equals V over D. Because that starts with voltage equals N, okay? So you can find the value of the electric field using that information. Now, from that, then you can go, oh, then I can feck it up because of the fact that now I know the value of my electric field. Do you know the value of the charge?
Of course. Oh, yeah.
Because it's an electron.
Yeah.
So you know the charge on an electron.
Yeah.
So then you can find the value of the force created by the electric field. That has to equal what?
Equal to magnetic.
And the force from the magnetic field is going to be what?
Bill. QVB.
QVB. Not Bill.
Not Bill.
Not Bill.
this time.
Why are we not using Bill?
It's not a wire.
It's not a wire. Yeah. And there's not a current. And there's not a length.
That makes sense.
Okay?
Sorry.
But now, this is going to be important later on. Why does the electron have to have a very, very, very specific velocity? Or can it just be random and have everything still work?
Repeat.
Why does the electron have to have a very specific velocity to send it through in a straight line?
Does it have something to do with mass?
No, has absolutely nothing to do with mass.
Attraction.
If it wasn't going that fast, it would go straight up.
Why?
Because this velocity and magnetic field.
Well, look at what determines the value of the force from the magnetic field. Okay, in a realistic lab situation, can you change Q?
No.
No, because it's an electron. That's kind of a fixed value.
If the velocity's too
Okay.
small, there's not enough force for.
Because if it's going too slow,
Yeah.
the force from the magnetic field is going to be less than the electric field. If it's going too fast, the force from the magnetic field is going to be too big. So you have to have that Goldilocks zone of just the right velocity. Therefore, these two values are the same. Now, here's the tricky part. Okay? So your answer for the value of the magnetic field should be a not so good GPA times 10 to the minus third. Okay? A not so good GPA times 10 to the minus third. Okay? Which is going to be the value of the magnetic field. Now, the tricky part here is the direction of the magnetic field. And it says you have to give that. Okay? What magnetic field strength and in direction will allow the electron to pass between them. So you have to give two parts to the answer. Okay? Now, here's the story. You know the force from the magnetic field has to act which way? Downward. But it's an electron. How do you want to play it? Do you want to play it with the right-hand rule and switch it, or do you want to use the left-hand rule?
Left-hand rule.
Okay, let's use the left-hand rule. So, my electron is going this way. which direction does the force in the magnetic field have to act? So my fingers have to act downward. So the only option is the magnetic field would be doing what?
Into the page.
Into the page. Okay? So you would have, in terms of a magnetic field, would you have X's or would you have dots inside of those?
I'd have some X's.
I'd have some X's. Now, this is where conceptually you have to think in 3 dimensions. So if this was what was actually happening, okay? So stay with me here. So here would be the 2 plates, like this, okay? You'd have the 2 plates like this. You'd have the positively charged plate at the top, the negatively charged plate at the bottom. You'd have this. Now, this is a little bit counterintuitive because you would think, oh, the magnetic field needs to be going up and down, okay, because it's like the electric field. No. The magnetic field would be acting like lines going this way. So the plates would be like this, but the magnetic field is going to be going at a 90-degree angle to like the plates. So the electric field is going to be acting up and down, but the magnetic field is going to be going like this. Okay? Common misconception, oh, the magnetic field has to be going up or down. The magnetic field will create a force that's up and down, but the magnetic field itself has to be going like this. Okay? So understand that visual. Okay. Now, let's talk about 44. That answer to 44 is a very, very small amount of force. The first non-zero digit should be a 2. Okay? Now, you be very careful about what I'm about to say. You be very careful and choose wisely. Your answer to 36 should be around my age.
46.
46.
56, yeah.
No comments.
That's why I said choose wisely.
Wait, you guys think
Yeah.
Shoes on saying that.
Oh my god.
Which one of these numbers looks like it's it ain't that one. It definitely ain't that one.
47 is around here.
Oh my god.
I was saying,
There's only one number on this page that could possibly be.
That's lost. Yeah, sorry.
There's only
I
one
would not
number.
form a question.
Okay,
It's
on
fine.
27.
Yeah.
So on 27, there's one assumption that you kind of have to make about these muons. Okay? And muons are they're there, but they're kind of weird. They don't exist very often. And the assumption that you have to make on 27 is that the radius is the same.
I just need the velocity.
Okay? You have to assume that they're orbiting with the same radius. That's the only way that you can begin to hope the math work out. And yes, the answer to 27 should be around my age if you're in kilohertz. So, now let's talk about question 21. Okay? So on question 21, this boils down to kind of a certain understanding of semantics. Okay? So on 21 it says an electron is moving in a circular orbit in the Earth's magnetic field directly above the north magnetic pole. Okay? So you have to start with this idea. Here's the Earth. It says the north magnetic pole. So we're saying that what that means is if you have a magnet at the Earth's surface, the North Pole is pointing in that direction. But what does that mean about the magnet inside the Earth?
The top is south, the bottom.
So what we call the North Pole is actually the
Magnetic
I know,
south.
but the
magnetic
first
south
straight
pole.
is at the
Okay.
Wait, what?
So here's the story. So now that we know that this is the South Pole, to answer this question, you have to know which direction the field lines are moving to answer this question. So, Sydney, what does this mean? Okay, you're conducting the magnetic field, okay? So the magnetic field is like the Confederate designation. Okay? So, the magnetic field lines
Wait. This is
at the North Pole
field.
are going inward.
Yeah.
Okay?
Wait.
So,
It's like
You're tired.
because if you run
if you're at the North Pole,
It says right there, North magnetic.
but to lift
the
it
field lines are pointing downward.
because
Now, you have an electron,
repel. You need it to go up.
not a proton. You have an electron.
But still,
So,
it's not a forcer.
Again, you can either use the right hand rule or you can use the left hand rule. I don't care. Alyssa.
I thought we were at the magnetic north.
You are, but that's what it's saying is that the Earth on 21, okay? So view from above, which is moving. So it's the North Magnetic Pole. So that's what we call the North Magnetic Pole is the South Pole because a magnet would be attracted. What?
Your drawing doesn't make sense to what you're saying.
Just change it to the.
Well, okay.
No, because then it still doesn't
When you
make
say
sense to
north
this drawing.
magnetic, do you mean I'm confused?
The
Okay.
North Pole is the South Magnetic. The South Pole, the thing that we call where the polar bears are at, is the North Magnetic.
Polar?
Okay.
We're still
So
talking about polar
listen
bears.
to me. On number 21, let's just step back for a second, okay? The North Magnetic Pole, okay? We're not saying the Earth's magnet. I'm saying what we as humans call the North Magnetic Pole. What we call the North Magnetic Pole
I gotcha.
is in reality the South Pole inside the Earth,
I'm there.
okay?
I got it.
So then, wait, but it's saying the magnetic pole, so wouldn't that mean the magnet?
We need a demonstration.
He just gave the demonstration.
Pull out your little Earth map.
If you have a magnet, okay, the little red end of that magnet is going to point towards the
We got
north,
different answers.
what we call north.
Yeah.
But that's actually the South Pole that's in the Earth.
South magnetic
So it's
pole.
not saying like, when it said magnetic, I thought it was talking about like we were talking about the magnet inside the Earth. Can you
No.
explain that to us?
No,
Does that not count
But-
clockwise?
because of the fact when it says the North
Look at the
Magnetic Pole,
Wait.
that's what
Because
we're
the thing
calling
is
the
that, like,
North
if it goes
Pole.
this
It's
way-
actually, we're talking about the
No, I'm
South
wrong.
Pole that's inside the Earth.
You're right.
Look at the
Okay?
No, I'm talking to myself. Or both of us, I guess.
Look at the clock.
So, you're talking about where Santa's workshop is. How about that?
Oh.
Yeah.
What? Now we're getting somewhere. So, which pole is under Santa's workshop? The South Pole is under Santa's workshop. So, Santa's workshop is at the North Magnetic Pole.
Yeah, that makes perfect sense.
You're right.
We love you, Bird.
Thank you, Mr. Brigham. Okay, can we ban this guy?
Oh, yeah.
The South magnetic.
Wait, Charles Sands.
It's like,
There's Santa's workshop.
Oh,
imagine
Yippee.
the-
thank you. That makes so much more.
Okay, just forget about the words.
And the lines are coming
Wait.
down into Santa's workshop.
That's for Santa.
That's why it's.
Yeah, there you go.
No,
Nice.
That's a good enough.
No,
Yeah,
that
it always goes one south.
Oh,
Salute.
That's it.
okay.
More.
Anyway, now that that's all established. God, that was a lot.
Let's do that.
On the multiple choice questions, 31 through 34, none of your answers should be C.
Okay.
I like that.
Hey, I like that. Where's this the oh
That sounds familiar.
yeah, that sounds familiar.
That sounds familiar.
That sounds familiar.
Into the plain of paper would be like sitting down into the page.
It's under the TV.
Certain by the
It's under the TV.
Wait, can you say that again?
34D into the plane of the paper would be
All right.
page.
Are we good?
Yeah. Okay.
Going once?
I said B thinking it was saying.
Huh?
Wait, I have questions.
Okay.
Can you do 24 and 25?
Can you do 31 and
Okay. So on problem 47,
3?
and this is why it's important that you have two springs, right? So here's spring number 1, here's spring number 2, here's the wire, right? So they are stretched by 1 centimeter. How big is the current? So here's the story. You have dots, right? Now, let's just think this through. Why you have the direction of the current, right? So, and you have, and again, you have to have 2 parts to this. You have to have a current, and you have to have a magnetic field. Either one of them by themselves will not create a force on a wire. You have to have a current, and you have to have a magnetic field. So, you have dots. So what's happening? Out. So if I took my thumb up, because that's the direction of the current, the magnetic field is coming out. So the force is acting to the right. So this is why it's stretching this spring. Okay? That's why it's stretching it. If the magnetic field had been going into the page, the springs would have gotten compressed. Okay? So this is getting stretched. Okay? Because that's the direction of the force. Cool with that. Now, if you look at what you're given on 47, so you've got 2 springs and you have the spring constant. So, if it was just, if you remember back to forces, how do you calculate the force to stretch a spring? Ks. Okay? Right? But, so you know what the spring constant is. That was given in the problem. You know how far it stretches, so you can figure out how much force it takes to stretch 1 string, but there's 2 of them, so you have to double it. So then you can go, okay, so now you know the total force that it takes to stretch the spring. So what you can do one of 2 things. You can either grab a hold of it and pull it, or you can let the current and the magnetic field do the work. So on 47, you know that force equals Bill. There we go. That's how you're going to get your force. Solve for the current. Does that make sense? Mara, which one did you want?
24 and 25.
Questions?
Yeah.
Okay.
I have some
So on question number 24. So the whole key to question number 24 is where this is happening. Okay? So here's the wire.
Oh yeah.
And you've got a dot. Okay? And you have the proton over here. Okay? So in this situation, you want to know how much force is there going to be. Well, in this situation, you have a dot. So which direction is it going? Out or in?
Oh.
So if you point your thumb out, right? So over here, if you wrap your hands around, at that point, because it's right over here, that is pointing upwards. That's also the direction of the magnetic field. Because if you do this, the magnetic field is going up like this. The velocity vector is also going up like that. So what's the angle between the field at that point and the velocity vector?
0.
0.
So there's no force.
So there's no force at all, because they're parallel with each other. Now, if it was up here, if the velocity vector was here, and, as that's going around, that would change. But at that point, it's just going to be parallel with each other. So there is no force. But now, if it had been going in like this, if that velocity vector had been pointing in like this, then there would have been a force.
So is 25 the same?
So on 25, it's a similar type idea, but not quite the same. So it's moving your long current carrying wire when the proton is at that point. In which direction is the force acting on it? So make sure when you get to question number 25 that you just don't say up or down. So help me, Nathan, do not give me cardinal directions on 25. On question 25. Okay? Don't do it. Don't do it.
They're in the same thing.
So yeah, 25 is a similar type thing. You're just trying to figure out where it's going to go. What?
So on 46, it asks for the direction of the magnetic field, not the force, right?
That doesn't mean it's the same.
The magnetic
It
field.
asks for the direction.
Okay, so it's going this way, right?
I
And
don't
it's gonna be going.
It asks for the direction of the magnetic field.
But I guess it
Okay. Mari, did that answer that question?
it helped with 24, not 25.
Okay.
Yeah, 25 is
So on 25, it's a similar type thought process. So the only difference is the location. So you got the wire here, and the proton is going up like this, right? Okay? So it wants to know in which direction is the force acting on it. So if you take your hand, right, and you do that right hand rule at that point, that force, that direction of the magnetic field is going to be going around like this. So you have to do this in a couple of steps. So this is going around like this. So what that gives you is the direction of the magnetic field. Okay? So you're like this. The magnetic field is going this way. That's your index finger. Okay? That isn't the force. That's the magnetic field. Okay? Your index finger is pointing this way. Your thumb is pointing up. Right? Which direction are these fingers pointing?
Down
No, don't say down.
into the
Say into the page. Because down, I think, is like this. It's going into the page. Okay? Popcorn?
question 31 and like for problem 33, like the direction. I'm confused on the direction.
On which one?
Problem 33. And
In
then,
terms of what?
like, is it, so it's talking about the magnetic field strength. Is that the force or just the magnetic field?
Are you talking problem 33 or question 33?
Problem.
So, what magnetic field strength and direction will levitate the 2-gram wire? So, again, on 33, it wants the direction of the magnetic field. Not the force, the direction of the magnetic field.
Yeah, I just realized that mechanic right now. And what about question 31?
Question 31?
Yeah.
Okay. So, on 31, that points directly between the two wires, the wire is done. Okay. So, you've got this, and you've got this, right?
Yeah.
So, what you want to look at is this. Start with this side. Which direction is the current going?
Counterclockwise.
Well, no, the current is going out of the page.
Yeah. Yeah.
So from that perspective, your thumb is pointing out. So when you get over here, which direction is the magnetic field?
Going up.
Going up. Then do the same thing with the X. So what's the X do?
Going like into the page.
Then it's just figuring out what's happening in the middle.
Okay.
They're either going to cancel each other out, or they at 90 degrees angle to each other, or they parallel. What are they doing?
They're both going up.
On the left.
Okay.
So, anything else? Going twice? So,
It's going.
Yeah.